Have you ever spent like 3 hours perfectly nudging a row of interface buttons, like by single pixels?
Oh, absolutely. We all have.
Right, you're double checking your math, you're zoomed in to like 800% to make sure everything's perfectly aligned.
And then you hand the file to a developer.
Yes. You hand it over, and they immediately point out that the entire screen just breaks the second someone opens it on a slightly smaller laptop.
It is the absolute worst feeling.
It really is. So, look, if you are listening to this right now, you might be staring at a messy canvas at this very moment, just wondering where it all went wrong.
Thinking you have to start over from scratch.
Exactly. Well, today we're going to look at why your beautiful interface design might actually be a structural house of cards, and more importantly, how to finally tame that chaos.
Yeah, because it's a painful rite of passage for almost everyone entering this field. I mean, we start out treating digital product design like we're painting a static portrait.
Like it's a poster or something.
Right, exactly. We place a rectangle here, we place some text there, we make it look aesthetically pleasing, and we call it a day. But a modern interface is not a painting.
No, it's alive.
It is a living, breathing, stretching organism. And if the underlying structural foundation isn't logical, well, the aesthetics simply don't matter. The design will shatter upon impact with reality.
That's a great way to put it. So welcome to today's deep dive. Whether you're just starting your graphic design career or maybe you're making that leap and transitioning into UI and UX design, consider today your ultimate foundation builder.
We are getting into the absolute essentials today.
We really are. We're going to show you how to pour the concrete, frame the walls, and wire the electricity of your design files so they literally never break again.
And we have some incredible source material for this.
We do. Our blueprint for this construction project is the Creating Layout chapter from an incredibly thorough book. It's called Designing in Figma, a masterclass in modern interface design.
It really is a masterclass. The level of detail is staggering. So good. And hey, if you're serious about mastering these technical weeds and leveling up your career, please make sure to follow the show for more technical design breakdowns and career-building content. We tackle these complex systems every week so you don't have to, decipher them alone.
Because doing it alone is just a recipe for burnout. So to build that foundation, we really have to start at the absolute microscopic level.
Okay, let's zoom all the way in.
Right. So the material we're referencing relies heavily on a methodology known as atomic design that was originally pioneered by Brad Frost.
Oh yeah, atomic design. That's a huge concept.
It's massive.
Yeah.
He basically recognized that designing a complex software system page by page was just inherently chaotic. It was too prone to inconsistency. So he looked at chemistry.
Chemistry. Okay, I love a good science analogy.
Yeah. Think about the physical universe. All complex matter is composed of basic atoms, right? So Frost just applied this exact logic to user interfaces. Okay, wait, let me make sure I'm visualizing this correctly. Like if I'm looking at my Figma canvas, a single solitary vector shaped like maybe a magnifying glass icon or a single text layer that just says search, those individual elements, are those the atoms?
Precisely. Those are your atoms. They are the smallest, indivisible units of your design. You can't break them down any further.
Right, because if you break the text down, it's just letters, which isn't a UI element anymore.
Exactly. But, an interface isn't just a bucket of loose atoms scattered around. We have to actually forge them together.
We have to make the molecules.
Right. You take that text atom, you place it next to the magnifying glass atom, maybe you put a rectangular background atom behind them both, and you bind them into a single functional unit.
So in Frost's methodology, that new unit, the search button itself, that's a molecule.
That is the molecule. Spot on.
And then I guess it just scales up from there, right?
Yeah.
I take that search button molecule, I place it next to, say, a navigation menu molecule and maybe a company logo atom, and suddenly I've built a website header.
Yes, and that header becomes an organism.
Okay, atoms, molecules, organisms.
And then that organism gets placed into a layout template, and eventually those templates become the final pages the user actually interacts with.
That's such a clean progression. I love that. But I feel like before we can even think about building complex organisms, we have to address these scattered atoms.
Oh, the messy canvas phase.
Exactly. Because when you're in the exploratory phase of a design, your canvas is usually just a total mess. You have dozens of icons, text snippets, and color swatches just dragged everywhere.
It looks like a tornado hit it.
It really does.
Oh.
And you cannot build a stable molecule out of loose components that are just floating randomly in space.
No, you can't. It's mathematically impossible to make it consistent.
It's exactly like trying to build a complex Lego castle. You don't just reach into a massive bucket of unsorted bricks, pull out a handful, throw them at the table, and hope they assemble themselves into a drawbridge.
That would be magic, not engineering.
Right. You have to sort the pieces, you line up the single pegs, you stack the flat plates, you have to create order. But honestly, doing that manually on a digital canvas is incredibly tedious.
Oh, it's soul crushing.
It is. I remember early in my career actually using a desk calculator to figure out the exact pixel coordinates to make sure 5 icons were evenly spaced. I mean, it felt like I was doing my taxes, not designing.
Yeah, the manual math approach is entirely unsustainable, especially when you're dealing with hundreds of screens. You'd never finish the project.
Exactly. So how do we avoid the calculator?
Well, Figma provides a suite of tools specifically designed to automate this initial sorting process. It starts with a function called distribute spacing.
Okay, distribute spacing. Walk me through it.
Let's say you have that row of 5 icons. They're overlapping, some are clustered together, others are far apart. It's just a visual mess.
But they generally form a horizontal line across my screen, right?
Correct. The first rule is that the objects need to overlap along a specific axis, so in this case, horizontally.
Okay, got it.
If you drag a selection box over all 5 of those messy icons, you can access the alignment menu and trigger distribute horizontal spacing.
And what actually happens when I click that?
The calculation Figma performs in the background is actually quite elegant. It looks at the object furthest to the left, then it looks at the object furthest to the right.
The bookends.
Exactly. It locks those 2 anchor points in place.
Yeah.
They do not move a single pixel.
Oh, I always wondered how it decided where to put everything. I thought it just averaged the whole group.
Nope. It uses the bookends. It measures the total available pixel distance between the inner edge of the left bookend and the inner edge of the right bookend.
Okay, so it finds the empty space.
Right. Then it takes the remaining 3 icons, calculates their widths, subtracts that from the total distance, divides the remainder by the number of gaps, and snaps the middle icons into perfectly even intervals.
Wow. And a process that would take me like 3 minutes of manual math happens in a literal millisecond.
Exactly. It's instantaneous.
Okay, but that solves a single row or a single column. What if the mess is two-dimensional?
Ah, like a grid.
Yeah, let's say I'm designing a photo gallery. I have 12 rectangular image placeholders, and I've just sort of loosely tossed them onto the canvas in a vague grid shape.
Right, some are overlapping, some rows are higher than others. Completely chaotic.
Exactly. Distributed spacing wouldn't work there because it only operates on one axis at a time.
Right. If you used it there, it would just collapse them all into a single overlapping row or column. It would be a disaster.
So what do I do for a 2D cluster?
For a 2-dimensional cluster, you need a slightly more intelligent algorithm. This is where the tidy up function comes into play.
Tidy up. I like the sound of that.
When you select that chaotic cluster of 12 images,
Yep.
a small grid icon will actually appear right in the bottom right corner of your selection boundary.
And when I click that little icon, Figma is essentially trying to read my mind, right?
Pretty much. It's running a heuristic analysis on the spatial relationship of all those objects. It looks at the rough X and Y coordinates of every item and deduces your intended rows and columns.
So it realizes, this designer is clearly trying to make a 3x4 grid.
Exactly. Tidy Up will then snap those objects into strict alignment. And unlike the simple distribute tool, Tidy Up might actually physically move the items on the outer edges to force them into a rigid, mathematically sound grid structure.
So it creates consistent horizontal and vertical gutters simultaneously.
Yes, all at once.
And honestly, getting them into that perfect grid unlocks a feature that brings me an immense amount of relief every single time I use it.
I know exactly what you're going to say.
Because when I was dealing with older, more rigid software, if I had a grid of 12 photos and the client said, actually swap photo number 2 with photo number 11, my heart would just sink.
Oh, the dread, because it meant manually dragging number 2 out, dragging number 11 up, moving the others out of the way.
And realigning everything from scratch. It was awful.
It was a fully destructive edit.
Yes. But once you use Tidy Up in Figma, you activate a system called Smart Selection.
And Smart Selection is a brilliant piece of interaction design.
It really is.
Right.
Explain how it works for the listener.
So once Figma recognizes that a group of objects shares perfectly consistent spacing, whether it's a single row or a full grid, it overlays a temporary visual interface.
The pink rings.
Yes, the pink rings. When you hover your cursor over the selection, bright pink rings appear in the exact center of each object. Additionally, thick pink lines appear in the negative space, the gutters between the objects.
Those pink indicators are essentially Figma whispering to you, hey, I understand the math here, let me handle the heavy lifting.
That's a great way to think about it.
Because if I click and drag the pink ring on photo number 2, I can just drag it over to the spot where photo number 11 is sitting.
And as you move it, the other photos in the grid literally part like the Red Sea.
Yes, they dynamically shift out of the way. And when I let go of the mouse, the 2 photos instantly swap positions. The perfect spacing of the grid is never broken.
And it extends beyond just swapping positions, too.
Oh, right, the pink lines.
Yeah, those pink lines in the gutters are draggable handles. You can click a horizontal pink line and drag downward to increase the vertical spacing between all the rows simultaneously.
So the entire grid just breathes and expands uniformly.
Exactly. Or you can grab the bounding box of a single photo, maybe make the featured photo slightly wider, and instead of overlapping the photo next to it, the grid just naturally pushes everything else outward to accommodate the new size.
It's incredibly fluid.
This fluidity represents a massive departure from legacy workflows. If you're transitioning from an older illustration tool, you really have to actively unlearn the instinct to manually nudge and babysit your layouts.
You have to trust the machine.
You do. Embracing the intelligence of smart selection fundamentally changes the speed at which you can iterate.
Okay, so we've taken our scattered atoms, we've analyzed them, distributed them, and tidied them up into a perfectly spaced arrangement.
They're sitting neatly on our workbench.
Right. But they're still just loose individual atoms. How do we actually bind them together?
That is the next logical step.
How do we declare to the software that these atoms now form a functional molecule? Because that transition brings us to the great divide in interface design, and honestly, the biggest point of confusion for anyone coming from a print or graphic design background.
You're talking about groups versus frames.
Groups versus frames.
It is absolutely the most critical conceptual hurdle you will face. If you do not internalize the distinct structural differences between a group and a frame, every file you build will eventually become unmanageable.
Okay, I'm going to push back here, or at least play the role of the stubborn legacy designer.
Let's hear it.
I have spent a decade living and breathing Adobe Illustrator and Photoshop. The keyboard shortcut Command-G is practically hardwired into my central nervous system.
It's pure muscle memory.
It really is. I select 5 shapes, I hit Command-G, they're bundled together, and I move them as one single unit. It works perfectly. Why on earth am I being told to abandon grouping when I move into UI design?
Because in the context of interface design, a group is functionally a ghost.
The ghost.
Yes. It is a legacy concept inherited from those exact illustration tools you mentioned. A group is nothing more than a temporary conceptual shortcut for selecting multiple layers simultaneously. That is its entire existence.
Wait, what do you mean it's a ghost? I can literally see it in my layers panel? I can click on it.
It appears in the panel, yes, but a group does not possess any intrinsic properties of its own. It has no physical boundaries. Its size, its width, its height, these are dictated 100% by the children inside it.
Okay, give me a visual example.
Sure. If you draw a red square and a blue circle, and you group them, the group itself does not have a background color, doesn't have borders. If you select that group and apply a yellow fill, Figma doesn't paint a yellow background behind the shapes. It actually reaches inside the group and forcibly changes both the red square and the blue circle to yellow. The group simply passes the command down.
Okay, let me try a physical analogy to see if I'm grasping this. A group is basically like taking a handful of random objects like a pen, a notebook, a coffee mug, and wrapping them tightly in industrial shrink wrap.
Shrink wrap, I like that.
The plastic wrap doesn't have a shape of its own, right? It just tightly hugs the contours of whatever happens to be inside it.
Exactly.
If I rip open the shrink wrap, add a massive textbook to the pile, and rewrap it, the overall bundle just stretches to become the exact size of the new pile. The wrap itself is doing nothing but holding them together.
That is a highly accurate mental model. The shrink wrap has no structural integrity whatsoever. Now compare that to a frame.
Right, if I highlight those same objects and hit Option-Command-G to wrap them in a frame instead, what structurally changes?
Literally everything. A frame is the foundational architectural unit of modern UI design. Unlike your shrink wrap, a frame is an adaptive structural parent container.
Okay, so it has its own structure.
Yes. It has strict, mathematically defined dimensions independent of its contents. A frame can have its own background color. It can have its own corner radius. It can have a stroke applied to its perimeter. It can even cast a drop shadow.
Building on my analogy then, if a group is formless shrink wrap, A frame is like placing those loose items into a sturdy, heavy-duty Tupperware box.
A Tupperware box, perfect.
The box has a defined length, width, and depth. It's made of solid blue plastic. If I put a tiny pen inside a massive Tupperware box, the box doesn't shrink down to hug the pen. It stays massive.
Exactly. And more importantly, extending your Tupperware analogy, that box has physical walls.
Right.
Because a frame has rigid, defined boundaries, it introduces a critical capability known as clip content.
How does that work in practice? Let's say I put a slice of pie in my Tupperware box, but the pie is 3 inches wider than the box itself.
Well, in physical reality, you would smash the pie against the plastic wall.
Gross, but accurate.
But in Figma, the wall of the frame acts as a precise surgical knife. If you place a wide image inside a narrower frame and you check the clip content box in the properties panel, anything that physically extends beyond the boundary of the frame is visually hidden.
Oh.
The data is still there, but it is cleanly masked.
That is the entire secret to designing scrolling interfaces.
It absolutely is.
Like if I'm designing a mobile app with a horizontal carousel of movie posters, the row of posters might be 1,000 pixels wide, but the iPhone screen I'm designing for is only 390 pixels wide.
Right, so if you use a group.
If I use a group, the posters just bleed out across my entire canvas, overlapping my other designs and making a massive mess.
Complete chaos.
But if I place that long row of posters inside a frame that is exactly 390 pixels wide and I turn on clip content, it instantly looks like a real constrained mobile screen.
Yeah.
The extra posters are hidden off screen, just waiting to be scrolled.
You absolutely cannot achieve that behavior with a group.
So when would I ever use a group?
Groups are meant exclusively for instances where you want complex vector paths to scale together flawlessly. For instance, the intricate curves that make up a custom illustration or a complex logo, those should remain a group.
Oh, okay.
That makes sense. But the moment you are constructing a functional UI element, a button, a navigation bar, a modal window, or an entire device screen, those must fundamentally be frames.
That makes total sense, but honestly, it introduces a major workflow friction point for me.
Let me guess, the layer labyrinth.
Yes. When I start nesting these Tupperware boxes, like I have an icon frame, inside a button frame, inside a header frame, inside a page frame, my layers panel turns into an absolute labyrinth.
It gets deep very quickly.
Navigating through 6 layers of nested frames to simply change the color of a single text atom feels like I'm digging a trench with a spoon. Double click, double click, double click. It is maddening.
Yeah, navigational friction will destroy your momentum. You have to bypass the structural hierarchy when necessary. The most important keyboard modifier you can learn here is the Command key on a Mac, or the Control key on Windows. If you hold that key down, your cursor enters a state we call deep select.
So it ignores the Tupperware boxes entirely.
Completely. With that key held down, a single click will pierce through every single nested parent frame and immediately select the exact deepest child layer your mouse is hovering over.
Just instantaneous surgical precision.
Exactly.
That saves hours over the course of a week.
But what if I want to navigate using just my keyboard? Sometimes moving the mouse back and forth to the layers panel breaks my focus.
Keyboard traversal is how the top 1% of designers move so quickly.
Okay, teach me the secrets.
If you have a parent frame selected, pressing the Enter key plunges you one level deep in the hierarchy. It instantly selects all of the direct children inside that frame.
Oh, it's like diving underwater. I hit Enter, and I'm swimming inside the box.
Yes, exactly. And if you want to surface back up for air, you just press Shift-Enter. That deselects the children and reselects the parent frame containing them. Enter to dive, Shift-Enter to surface.
Got it. Furthermore, once you are inside a frame, you can use the Tab key to cycle sequentially through the sibling elements, and Shift-Tab to cycle backward. Your hands literally never have to leave the keyboard.
I love that. Dive in with Enter, swim around with Tab, surface with Shift-Enter. But, and there's a big but, there's one specific behavior regarding frames that used to make me want to throw my laptop out a window before I learned how to control it.
The auto-nesting?
Yes. Because a frame is essentially an open Tupperware container, Figma aggressively assumes you want to put things inside of it.
It is designed to be helpful, but it can be intensely frustrating.
Highly frustrating. Let's say I have a tiny floating action button. I just want to drag it across my canvas to park it near my design library. As I drag it, my cursor passes over a massive desktop web page frame.
And it eats it.
The second I hover over it, Figma highlights the big frame in blue, swallows my button, and rips it out of its original layer hierarchy to nest it deep inside the desktop page. My layers panel is ruined, and I have to manually drag it back out. How do I stop the container from eating my elements?
The escape hatch is the spacebar.
The spacebar.
Yes. When you click and begin to drag an object across the canvas, press and hold the spacebar. That keystroke temporarily disables Figma's auto-nesting algorithm.
Oh, wow.
You can smoothly drag your button directly over the most complex, deeply nested frames, and it will simply float above them like a ghost. When you drop it, it remains exactly where it was in your layer hierarchy.
That is amazing. It's a tiny mechanical detail, but mastering it is essential for your sanity.
Absolutely. Okay, so we've established that frames are rigid structural containers. We can dive into them, we can float over them, but the reality of our industry is that we don't just design one static container anymore. We don't design for a single screen size. We design a dashboard, and the user might view it on a tiny 13-inch laptop, or they might stretch the browser across a massive 32-inch ultra-wide monitor.
Right, responsive design.
Yes. If our Tupperware box gets stretched to twice its width, what happens to the perfectly arranged molecules inside it?
They usually break.
Exactly. This brings us to the rules of responsiveness, constraints, and layout grids.
Okay, let's unpack this. This is exactly why the transition from groups to frames is mandatory.
Right. Because a frame has defined physical boundaries. A top, bottom, left, and right edge Figma can utilize those edges as mathematical anchor points for the objects inside.
And this relationship is governed by a system called constraints.
Correct.
So constraints are basically a set of instructions. I'm selecting an atom, and I'm telling it exactly how it should behave if its parent frame gets stretched or squished. When I select an object inside a frame, a small diagram appears in the Properties panel with these blue dotted lines. How do I read this diagram?
The diagram represents the X and Y axes. By default, Figma applies a top and left constraint to every new object.
Top and left. Okay.
This means the object measures its exact pixel distance from the top edge and the left edge of its parent frame, and it will fiercely protect those distances. If you stretch the frame 500 pixels to the right, the object doesn't care. It remains anchored to the top left corner.
Which is fine for, like, a logo in the top left corner. But what about the other options? Let's talk through a scenario where a design completely fails without constraints.
Okay, set the scene.
Imagine I'm designing a standard app header. It's a horizontal bar. On the far left, I have a hamburger menu icon. Right in the dead center, I have the title of the screen. Let's say it just says Inbox. And on the far right, I have a magnifying glass search icon.
A completely standard structural pattern. We see it everywhere.
Right. Now, if I highlight those three elements and just hit Command-G to group them, acting like I'm still in Illustrator, and then I try to stretch that header from a narrow 320 pixel mobile screen to a 768 pixel tablet screen, disaster strikes.
The group has no anchor points. It only knows how to scale proportionally.
Exactly. The hamburger icon stretches horizontally and becomes a fat, distorted smudge. The word inbox physically stretches out, and the typography is completely ruined. The search glass turns into an oval. It is unusable.
It looks awful. So how do constraints prevent this structural failure?
Well, we dismantle the group and place those three elements inside a proper header frame.
Yes. Then we assign specific behavioral rules to each element individually. You select your hamburger menu icon on the left. In the constraints panel, you pin its horizontal axis to the left and its vertical axis to the center.
Okay, so it will always stay exactly, say, 16 pixels away from the left wall, and it will always float perfectly in the vertical middle of the header bar, even if the header gets taller.
Precisely. Then you select the magnifying glass on the right. You pin its horizontal constraint to the right and its vertical to the center. Now it will always measure its distance from the right-hand wall.
And the inbox title.
You set its horizontal constraint to center. It will ignore the left and right walls entirely and continuously calculate the mathematical midpoint of the parent frame, anchoring itself there.
So now, when I grab the right edge of that header frame and drag it across my screen to simulate a massive tablet display, the hamburger icon stays securely locked to the left wall. The search icon travels smoothly across the screen, locked to the right wall. The title floats perfectly in the center.
And the empty space between them dynamically expands, but the elements themselves do not stretch, distort, or break.
The design is now fully responsive.
You have engineered a resilient component. However, there is a common workflow trap here.
Uh-oh, what is it?
What if you are designing a long, scrolling web page? You have carefully set up dozens of complex constraints for all your cards and navigation bars, but you run out of vertical room on your canvas. Oh, I hate when that happens.
You simply need to drag the bottom edge of your main page frame down to give yourself more empty space to design the footer.
Oh, I know this pain intimately. If you just grab the bottom of the frame and pull it down, Any object that you had constrained to the bottom or the center vertically will suddenly be dragged down the page with your cursor.
Yes, your entire layout shifts and breaks just because you wanted a larger canvas.
The constraints are dutifully following their instructions, but you don't want them to right now.
Precisely. So the trick here is another brilliant keyboard modifier. If you hold down the Command key on Mac or Control on Windows, while you click and drag the edge of a parent frame, Figma temporarily deafens the constraint engine.
It just completely ignores all the rules.
It does. It physically extends the size of the Tupperware box, leaving every single object inside exactly where it was. You can add 3,000 pixels of empty space to the bottom of your web page without disrupting a single pixel of your existing layout.
It is a critical maneuver for document management. Honestly, life-changing. It really is. Now, constraints are incredibly powerful for pinning objects to the perimeter of a container. But what if your layout requires a more complex proportional structure?
Like what?
What if you are designing an e-commerce grid with 4 columns of product cards, and you need them to scale and reflow predictably across different devices? Simple edge constraints are not intelligent enough to handle complex subdivisions.
Right, because there are elements in the middle of the screen, not just the edges.
Exactly. That requires the implementation of layout grids.
Grids, they are the invisible scaffolding of the design world. And I love the historical context provided in the source material because it proves that we aren't just making these rules up as we go. The concept of the grid didn't originate in software.
Far from it. To understand modern UI grids, you really have to look back to the post-World War II era, specifically mid-century Swiss graphic design.
Really? Like posters and stuff?
Yes. Typographers and designers like Joseph Müller-Brockmann revolutionized visual communication by introducing strict, mathematically rigid grid systems to lay out posters, books, and magazines.
Okay, so applying strict math to art.
They realized that by dividing a blank page into a uniform mesh of columns and rows, they could create layouts that were inherently balanced, highly legible, and modular. It became the absolute gold standard for the print industry.
But there is a massive fundamental difference between a printed poster and a digital interface. A poster is static. Once it's printed, the paper never changes size. The grid is locked in ink.
Right.
But a web browser is incredibly hostile to static layouts. A user can grab the corner of their browser window and drag it to any arbitrary dimension they please.
And that was the defining crisis of early web design. In the late 90s and early 2000s, designers were still thinking like print designers. We built fixed pixel grids. We explicitly told the code this column is exactly 200 pixels wide.
And when a user viewed that site on a smaller monitor,
The design didn't adapt, it just broke. It forced the user to painfully scroll horizontally to read a single paragraph.
it was a terrible user experience. I remember those days.
It was. The paradigm shift occurred in 2009 when a designer and developer named Ethan Marcotte published a seminal article in a Listapart titled Fluid Grids.
Fluid grids.
He proposed a radical idea. Stop using fixed pixels. Instead, define the grid mathematically using percentages. Instead of saying a column is 200 pixels, you tell the code the column should be 25% of the available screen width.
And responsive web design was born. The grid became elastic.
Yes, it was a monumental leap forward for engineering. However, the design tools of that era were completely unequipped to visualize this. We were still drawing static, fixed rectangles in Photoshop.
Right, we had to manually calculate the percentages and hand a static picture to a developer, hoping they understood our intent.
Figma solved this disconnect by building fluid layout grids natively into the Canvas rendering engine.
Okay, let's break down exactly how these tools work in Figma, because they are incredibly robust. You can apply a layout grid to any frame. And because we know frames can be nested inside other frames, you can have a massive 12-column grid applied to your entire desktop web page frame, and then inside one tiny product card frame, you can apply a completely different microscopic uniform grid.
The modularity is limitless. Figma basically categorizes grids into 3 distinct types: the uniform grid, columns, and rows.
Start with the uniform grid.
The uniform grid is the simplest. It simply overlays a piece of graph paper over your frame, a continuous mesh of tiny squares.
By default, Figma sets those squares to 10 pixels by 10 pixels. But the source material, and frankly the entire modern tech industry, strongly advises abandoning the 10-pixel grid.
The 10-pixel base is largely considered obsolete. The industry standard has almost universally adopted the 8-point grid system. That's a framework heavily popularized by Google's material design guidelines.
Why the number 8? I mean, it seems arbitrary. Why not 10 or 5? We have 10 fingers.
It comes down to screen resolution mathematics. Digital displays render graphics using pixels. When screen resolutions began to multiply, going from standard definition to Apple's Retina displays, which pack twice or 3 times as many pixels into the same physical space, the rendering engines had to scale the graphics mathematically.
Okay, so there's math involved.
If you have an object that is 5 pixels wide and the screen tries to scale it by 1.5 times, you get 7.5 pixels.
And you cannot display half a pixel. A pixel is a pixel.
Exactly. The screen tries to guess, resulting in a blurry, anti-aliased, muddy edge. But the number 8 is a magical number in binary-based systems. It divides cleanly by 2 and 4. It scales perfectly.
Oh, that makes so much sense.
By enforcing a rule where every single measurement in your design, every margin, every padding, every button height, every icon size is a strict multiple of 8, you guarantee that your design will render with absolute mathematically crisp perfection across every conceivable device resolution. 8, 16, 24, 32, 64. That is your new vocabulary.
And for smaller, more delicate elements, like adjusting the baseline of typography or nudging a tiny vector point inside an icon, you drop down to a 4-pixel subgrid. It still scales cleanly, but gives you finer control.
Yes, the 4-pixel subgrid is essential for typography.
But to actually work at this speed, you have to reprogram Figma's default behavior.
You absolutely must synchronize your tools with your mental model. When you select an object on the canvas, hold down the Shift key and press an arrow key, Figma performs what is called a big nudge.
Which is so handy.
By default, it moves the object exactly 10 pixels. But if you are trying to adhere to an 8-point system, a 10-pixel nudge will instantly destroy your mathematical alignment.
You will literally spend your whole day tapping the arrow keys backward to correct it. 10 minus 2 over and over again. The fix is to dive into Figma's core preferences menu and permanently change the big nudge amount from 10 down to 8.
It takes 5 seconds to change.
Once you do that, you can fly across the canvas. Shift right, shift down, and you know with absolute certainty that your object is resting perfectly on the 8-point mathematical grid. It is incredibly satisfying.
It eliminates the cognitive load of constant measuring. You just trust the nudge. Now, the uniform grid is excellent for spacing, but it does not solve the fluid responsiveness we discussed earlier. For that, we turn to columns and rows.
This is where we mimic how the web actually works. If I apply a column grid to a frame, I have 2 choices. I can set the columns to be fixed, meaning I dictate that they are exactly 60 pixels wide, and they just sit rigidly in the center of the screen.
Which is fine for some static layouts.
Right. But the real magic happens when I change the type from fixed to stretch.
Setting the columns to stretch engages the fluid layout engine. Let's construct a scenario. You have a main container frame. You apply a 4-column stretch grid. You tell a grid you want a 16-pixel margin on the far left and right edges, and you want a 16-pixel gap, which we call a gutter between each of the 4 columns.
So the margins are locked at 16, and the 3 gutters are locked at 16. What happens to the actual columns themselves?
The algorithm calculates the total width of the frame, subtracts the locked margins and the locked gutters, and then divides whatever pixel space is left over equally among the 4 columns.
Wow.
As you grab the edge of that parent frame and drag it to simulate a wider monitor, the margins stay perfectly frozen at 16. The gutters stay perfectly frozen at 16, but the red columns dynamically expand and stretch like rubber bands to consume the extra space.
It perfectly mirrors Ethan Marcotte's fluid web principles. But here is the absolute wildest part of this entire system. This is a mechanic that blew my mind when I first read about it, because it feels like a hidden cheat code.
I know exactly what you're talking about.
There was an undocumented synergy between these fluid layout grids and the basic constraints we talked about earlier.
It is arguably one of the most powerful yet least discoverable features in the entire application. It requires a deep understanding of both systems to exploit.
Let's set up the failure state first so people understand why this is so cool. I have a wide parent frame. Inside it, I place 3 square product photos next to each other. I want them to stretch when the screen stretches. So I select all 3 photos, and in the constraints panel, I set their horizontal constraint to left and right.
Okay. In a standard scenario, without a layout grid, the left and right constraint forces the object to anchor its edges to the absolute outer walls of the parent frame.
Right. So it calculates the distance from the left wall and the distance from the right wall and locks them. Now, when I stretch the parent frame wider, the 3 photos do indeed stretch horizontally. But the negative space, the gap between the photos, stretches too.
Yes.
My perfect 16-pixel gap distorts and turns into a massive, ugly 80-pixel chasm. The design completely loses its structural integrity.
Because the constraints only know about the outer walls. They do not know about the objects next to them.
But if I rewind, before I stretch the frame, I apply a stretchy column layout grid to that parent frame. I set up my columns, and I ensure my 3 product photos are physically snapped to align with those columns.
You are introducing an invisible skeletal structure into the Tupperware box.
Exactly. Now, with that grid active in the background, if I select my 3 photos and apply that exact same left and right constraint, Figma fundamentally changes how the math works. The photos no longer anchor to the outer walls of the parent frame.
The constraint algorithm detects the presence of the layout grid and intelligently intercepts the command. It tells the objects to anchor their left and right edges to the nearest boundary of the column they are sitting inside, rather than the frame itself.
It is pure magic, because the layout grid is fiercely protecting those 16-pixel gutters, making sure they never stretch. The photos inside the column stretch beautifully as the screen gets wider, but the space between them remains locked at a crisp, mathematically perfect 16 pixels. You have achieved true, code-accurate responsive scaling without writing a single line of CSS.
It bridges the gap between static drawing and dynamic engineering. It's beautiful. However, as brilliant as fluid grids are for simulating responsive behavior, there are moments in the product development lifecycle where fluidity is actually a liability.
Wait, really? When is fluidity a liability?
When you are finalizing a design to hand off to a development team, they cannot code a vague concept of stretchiness without exact baseline parameters. Sometimes you need microscopic, manual, absolute precision. You need to declare exactly how many pixels exist between point A and point B.
Okay. That brings us to section 4. The pixel-perfect handshake rulers, guides, and handoffs. Fluidity is great for exploring ideas, but eventually you have to draw a hard line in the sand and write the manufacturing specs.
Engineering requires exact specifications. To achieve this manual precision, we utilize the oldest drafting tools in existence, digitized. By pressing the keyboard shortcut Shift-R, you summon the rulers, which appear along the top and left margins of your vast canvas.
And from those rulers, you can click and drag downward or rightward, pulling out these incredibly thin, bright red lines called guides. You drop them onto your canvas to create strict, custom alignment points that don't conform to a standard mathematical grid.
But the implementation of guides in modern tools has a very specific hierarchy that you must understand. If you pull a guide down and drop it onto the empty gray background of your canvas, you have created a global guide.
Global guide, meaning it's everywhere.
Yes. It exists independently of any design. It is locked to that exact coordinate in infinite space.
Which is helpful if you are lining up several different artboards in a row. But usually I need a guide to measure something specific inside my mobile app screen.
In that case, you must drag the guide and deliberately release your mouse while hovering inside the boundary of a specific top-level parent frame. When you do that, the guide becomes localized. It becomes a permanent child of that specific frame.
So if I decide to reorganize my canvas, and I drag my entire mobile screen 1,000 pixels to the right, that red guide travels safely inside the frame with it, maintaining its exact relative position to my buttons and text.
It ensures your measurements are not destroyed by simple file reorganization.
Okay, so localized guides are fantastic for me while I'm actively pushing pixels around. They help me ensure my typography baselines are perfectly aligned. But I hit a massive wall with this early in my career. And the book specifically calls out this exact friction point.
Handoff issues.
Yes. When I'm done designing, I send a link to this Figma file to my lead developer. I expect them to look at my red guides and understand my intent. But the native Figma guides are essentially invisible to the developer's inspection tools. They do not export into formal documentation. So how does the developer know what my invisible guide was meant to communicate? How do they know I intended exactly 24 pixels of padding beneath that headline and not 22?
This is where the design process often breaks down into frustration and resentment. If a developer has to guess your intent, or if they have to manually measure your canvas because your structural logic isn't explicit, the design has failed its primary communication objective.
It's just a pretty picture at that point.
A design file is not just a picture, it is a set of instructions. The source material introduces a highly effective cultural and technical solution to this, the Redlines plugin.
Redlines. This plugin completely changed my relationship with my engineering team.
To understand the plugin, you have to understand the terminology. In traditional print design and architectural drafting, a red line was a literal physical document.
Like actual red ink on paper.
Yes. A senior designer or architect would take a finished proof, uncap a bright red pen, and draw lines, arrows, and exact measurements all over the page to instruct the printer or builder on the exact specifications. It was the undeniable source of truth.
The Redlines plugin brings that exact physical workflow directly into the digital Figma canvas. It allows you to permanently annotate your mockups.
Instead of relying on invisible native guides, you select an object on your canvas, invoke the Redlines plugin, and it will physically draw highly visible red measurement lines and brackets. It will explicitly write the pixel distance between that object and the edge of its parent frame directly onto the canvas.
It removes the guesswork entirely. I don't just say, make it look like this. I run the plugin, and it draws a bright red bracket that physically says 24px right next to the padding. It can outline the bounding boxes of complex invisible components so the developer knows exactly how large the hit area for a button should be.
It shifts the burden of measurement from the engineer back to the designer where it belongs. You create a dedicated page in your file specifically for handoff. You place your finalized, approved screens there. You run the Redlines plugin over them, heavily annotating the critical, complex layouts.
You are handing the developer a pixel-perfect, fully annotated map.
It is the definitive handshake between design and manufacturing.
Okay, so we've spent so much time talking about manual precision, measuring gaps, drawing red lines, and setting up strict constraints. But what if there was a way to make the design essentially layout itself?
That is the dream, isn't it?
It is. What if we could build a Tupperware box that was so incredibly smart, it automatically calculated its own size, distributed its own internal spacing, and dynamically adjusted whenever the content inside it changed, without us ever having to drag a single edge or draw a single red line?
You are describing the absolute zenith of modern interface design tools. You are describing auto layout.
I'm so excited for this section. If you are listening to this and you haven't mastered auto layout, I promise you, this is the concept that will double your salary. This is the heavy machinery.
Auto layout is not just a feature, it is a complete paradigm shift in how you conceptualize digital space. It takes every single concept we have discussed so far, alignment, distribution, constraints, and fluid grids, and completely automates them through a rigorous set of mathematical rules.
The source material is very explicit about where these rules come from. It notes that auto layout is directly built upon the CSS Flexbox paradigm. Now, a lot of UI designers do not write code. If I have zero background in web development, what does Flexbox actually mean in plain physical English?
Flexbox, which stands for Flexible Box Layout, is a standard rendering module in CSS, the code that styles websites. It was designed specifically to solve the nightmare of distributing space dynamically among items in a container, especially when you don't know exactly how big those items are going to be.
So if I don't know if a user's name is Bob or Christopher, Flexbox handles the math so the UI doesn't break.
Precisely. Let's use a physical analogy. Imagine a standard string threaded through a handful of large wooden beads. That string is the Flexbox axis. You can pull the string perfectly tight horizontally, you can let it hang vertically, you can squeeze all the beads tightly together at one end of the string, or you can tell the beads to space themselves out evenly along the entire length of the string.
But no matter what you do, the beads are inextricably bound to the path of that string. They cannot float away.
They surrender their independence to the string.
Exactly. Auto layout is simply Figma taking that exact mathematical CSS string and embedding it directly into the visual interface. When you use auto layout, you are fundamentally writing Flexbox code visually. If you understand how auto layout behaves, you implicitly understand how modern web engineering works.
And applying this string to our designs is shockingly simple. You just highlight a frame or even a messy cluster of objects and hit the keyboard shortcut Shift-A. The transformation is instantaneous.
And going back to our earlier debate about groups versus frames, if I make the mistake of highlighting a group and hitting Shift-A, Figma immediately destroys the group and upgrades it into a frame.
It has to. Because auto layout is a complex system of internal rules, it requires a structural container to hold those rules. It needs the rigid properties of the Tupperware box. The formless shrink wrap of a group simply cannot compute the mathematics of Flexbox.
Once you hit Shift-A and apply auto layout, the physics of your canvas change completely. You have to start thinking in a hierarchy of parent controls and child behaviors. Let's examine the parent frame first, because the parent dictates the flow of the string.
In the Properties panel, the parent frame exposes several core levers. The first is direction. You must declare the axis of your string. You can set the frame to flow horizontally from left to right. This is exactly what you would use to build a row of social media icons or a top navigation bar.
Or I can set it vertically.
Right. Alternatively, you can set the flow to be vertical from top to bottom. This is how you construct a scrolling newsfeed or a drop-down menu or a stack of text paragraphs.
Next comes resizing, which is where the true automation happens. You have to explicitly tell the parent auto layout frame how it should react to the objects living inside it. And you have a couple of options here.
The most powerful setting is hug contents. When a parent frame is set to hug, it effectively acts like a dynamic shrink wrap, but with mathematical rigidity. The frame continuously calculates the total width and height of every child object inside it, adds them together, and dynamically snaps its own outer boundaries to perfectly wrap around them.
This is the secret to unbreakable buttons. If I design a button and set the parent frame to hug contents, it wraps tightly around the text label. If the label says OK, the button is tiny. If I click in and change the text to acknowledge and continue, the parent frame instantly calculates the new longer text width and automatically stretches the entire button wider to accommodate it. I never have to manually drag the edge of the button again.
It is entirely self-regulating. Alternatively, you can set the parent's resizing to fixed. In this state, the parent frame remains a strict specific dimension, say exactly 300 pixels wide, and the child objects must negotiate how to distribute themselves within that locked space, often wrapping to a new line if they run out of room.
And to control the breathing room inside that box, we use padding and spacing. Padding is the invisible protective force field on the inside walls of the parent frame. If I set the padding to 16 pixels, it forces all the content to stay at least 16 pixels away from the edges.
And spacing between is the exact pixel distance forced between each individual child object on the string.
Okay, so these are the parent controls. But here is the critical pivot where beginners often panic. By applying these automated rules to the parent, you systematically strip away the manual freedoms of the child objects.
Yes, you have to surrender control to the machine. The source material is adamant about clearly defining what you lose when an object becomes a child of an auto layout frame. If you try to click a bead on the string and just drag it freely to the top right corner of the box, you can't. The system physically prevents me.
You lose manual X and Y coordinate positioning. The auto layout engine completely monopolizes the positioning mathematics. You also lose access to the standard constraints panel we discussed earlier because the Flexbox rules supersede them. And those delightful pink smart selection rings, they vanish.
Because the system is already perfectly spacing everything, so the manual smart selection is redundant. I remember turning on auto layout for the first time, trying to drag an icon a few pixels to the right and feeling incredibly restricted. Why would I willingly give up that control? What do I get in return for surrendering to the string?
You get absolute systemic consistency, which is far more valuable than manual freedom. In exchange for free positioning, the children are granted alignment and order controls. You can select a child object and tell it to align to the center, the top, or the bottom of the cross-axis.
And the true power lies in reordering. Because the items are locked to a sequence, you simply select an item and press your left or right arrow keys. The item instantly jumps over its neighbor, rearranging the sequence, and the auto layout engine perfectly recalculates all the spacing and padding in a fraction of a second.
And that alignment is persistent. If I tell a tiny checkmark icon to stay perfectly vertically centered next to a text paragraph, it stays locked to the center. If my client adds 3 more sentences to that paragraph, pushing the text box taller, the auto layout engine instantly detects the new height and dynamically pushes the checkmark icon down to perfectly maintain that mathematical dead center alignment. Doing that manually across 100 screens would take hours.
The time savings are exponential. Now, speaking of the sequential order of elements, we must address the controversy.
Well, the reverse layer order controversy. I genuinely love the drama behind this. It highlights how deeply passionate designers get about structural logic.
It is a fascinating case study in what happens when human cognitive psychology clashes directly with software engineering architecture. The book heavily references a famous Twitter thread authored by Sho Kuwamoto, who is the director of product at Figma. He had to publicly explain why the engineering team made a highly controversial, seemingly illogical decision regarding how auto layout structures layers.
Okay, let's set the scene for the listeners so they can feel the frustration. Imagine I create a brand new vertical auto layout frame on my canvas. I want to make a simple list. I add 3 text boxes inside it, stacking them top to bottom. Visually, on the white canvas, I read them sequentially from the top down. Item 1 is at the top, item 2 is in the middle, item 3 is at the bottom. It makes perfect logical sense.
Because in the Western world, we read left to right, top to bottom. That is our ingrained mental model for processing lists.
Exactly. But when I take my eyes off the canvas and look over at my layers panel on the left side of the screen, the list is completely upside down. Item 1, the top element visually, is sitting at the absolute bottom of the layer stack. Item 3, the bottom element visually, is sitting at the very top of the list. It feels completely broken. I used to manually drag the layers in the panel to put item 1 at the top, only to watch my visual canvas slip upside down. Why on earth would the layer panel show a list bottom to top when we read top to bottom?
It seems like a glaring bug until you unpack the fundamental architecture of digital rendering space. Kuamoto explained that the engineering team was forced to make a compromise to preserve the traditional behavior of the z-axis.
The z-axis being physical depth, what object is sitting in front and what is hiding in the back.
Precisely. In literally every digital art program created since the 1980s, Photoshop, Illustrator, MS Paint, when you draw a shape and then you draw a second shape, the newer shape is placed on top of the older one visually. It obscures it. Therefore, to represent this physical stacking order, the Layers panel always places the newest object at the top of the list. Top of the list equals front of the screen. Bottom of the list equals back of the screen.
Okay, that makes sense for drawing overlapping circles, but auto layout items generally don't overlap. They sit next to each other.
True, but the underlying rendering engine doesn't differentiate. Auto layout forces a strict synchronization between the visual layout on the canvas and the structural hierarchy in the Layers panel. Figma treats the very first item you place in an auto layout sequence as the foundational item. It is the base. Any subsequent item added to the sequence is mathematically treated as being placed on top of the stack in the z-axis, even if the auto layout rules force it to sit visually below it on the y-axis.
So because item 3 was the last thing added, the rendering engine considers it the top layer in physical space, so it must go to the top of the Layers panel list to maintain consistency with the rest of the software.
Exactly. The engineering team realized that if they flipped the layer panel to match the top-to-bottom reading order just for auto layout frames, they would break the fundamental, decades-old rule of how the z-axis is represented. If you gave those auto layout items a negative spacing value, so they actually overlapped, suddenly the layer at the bottom of your panel would be overlapping the layer at the top, creating immense confusion for anyone used to standard layer behavior.
Is a classic dilemma. Engineering truth versus human reading patterns. They chose to maintain the integrity of the z-axis across the entire application, rather than creating a special contradictory exception just for auto layout. It's wildly confusing the first 10 times you encounter it, but once you understand why it works that way, you stop fighting the machine and accept the logic.
Once you accept the system, you can start pushing its boundaries. And one of the most critical nuances to master within auto layout is its relationship with typography. Text layers behave uniquely inside these automated systems.
I found the analogy used in the source material to be incredibly profound here. It suggests that you shouldn't just think of text as a static object. You should think of a text block as essentially being a miniature, invisible auto layout frame specifically designed for words.
It is a brilliant mental model. Text inherently acts like flexbox. It flows, it wraps, it expands. Text layers in Figma have 3 specific resizing modes that directly mirror auto layout behaviors: fixed size, auto width, and auto height.
Let's break those down. If I draw a text box and set it to fixed size, I am forcing it to behave like a rigid, dumb rectangle. I have to manually grab the edge of the text box and drag it to make it wider or taller. If I type a paragraph that is too long for the box, the words just awkwardly bleed outside the invisible boundaries or they get chopped off. It ignores the content entirely.
It behaves identically to a standard parent frame set to fixed resizing. It provides no automation.
But if I select that text layer and change its mode to auto width, the behavior completely transforms. The text box loses its rigid right edge. It will now endlessly stretch horizontally in a single unbroken line to accommodate every single character I type. It will literally stretch off the canvas if I don't hit the return key.
That horizontal stretching is exactly how a horizontal auto layout frame behaves when its resizing is set to hug contents. It simply grows to wrap the sequence.
And finally, there's auto height. The text box locks its horizontal width, say, to 400 pixels wide, but it unlocks its bottom edge. As I type, the words hit that 400 pixel wall, automatically wrap to the next line, and the entire text box dynamically pushes its bottom edge downward to wrap the new paragraph. It grows vertically based on the content.
Which perfectly mimics a vertical auto layout frame set to hug contents. The critical takeaway for a designer is that the internal gears of your text layers must synchronize with the external gears of your auto layout component.
This is where components break. I see this all the time. A junior designer will build a beautiful, perfectly automated auto layout button. They set the button to hug contents horizontally, but they accidentally leave the text layer inside the button set to fixed size.
A fatal mechanical error.
Yes, because the text layer is rigid, it cannot grow. So when the client asks to change the button text from buy to add to shopping cart, the text just spills outside of its internal fixed box. Because the text box didn't physically get wider, the parent auto layout button doesn't detect any change in size, so the button doesn't stretch. The automation is broken by a single faulty gear. You must set the internal text layer to auto width so it pushes against the walls of the auto layout parent, forcing the parent to expand.
You have to ensure the kinetic energy flows seamlessly from the inner atom all the way up to the outer organism. Now let us tackle a real-world layout problem that exposes a limitation of this automation and how to creatively bypass it.
I know exactly what you were going to bring up: the tyranny of uniform spacing.
Precisely. Auto layout, by default, enforces mathematical uniformity. If you create a vertical layout containing a headline, a paragraph of text, a large feature image, and another paragraph of text, you use the spacing between property to push them apart. Let's say you set the spacing to 16 pixels.
Right, the Flexbox string forces exactly 16 pixels between every single item.
Visually, 16 pixels of space between a headline and a paragraph looks perfectly tight and readable, but 16 pixels of space above and below a massive feature image is completely insufficient. The layout feels claustrophobic and cramped. The image needs 48 pixels of breathing room to stand out. But you cannot tell the auto layout engine, give me 16 pixels here, but 48 pixels there. It is an all or nothing setting. How do we break the uniformity without breaking the automation?
I will admit, my early attempts to solve this were embarrassing. I tried wrapping the image inside another nested auto layout frame and applying extra padding just to that new frame to force the space. It technically worked visually, but my layers panel became a nested nightmare of useless, empty containers. When my developer inspected the file, they saw a maze of empty div tags that made absolutely no semantic sense in the code. I'd corrupted the file just to get a visual gap.
A very common destructive workaround. But the source material outlines a vastly superior, highly elegant solution for irregular spacing. It involves a counterintuitive first step. You set the master spacing between value on your parent auto layout frame to absolute 0.
You completely turn off the uniform gaps. So now my headline, my text, and my image are all smashed tightly together, physically touching.
Yes. You have removed the automated spacing. Now you manually inject space exactly where you want it by creating custom spacer components.
This is such a clever hack. You literally use the shape tool to draw a physical rectangle on the canvas. You set its width to fill the container, and you set its height to exactly the gap you need, say 16 pixels. Then you draw another rectangle and set its height to 48 pixels. You have physically materialized your negative space into actual objects.
You are creating invisible Lego bricks whose sole purpose is to occupy physical volume on the string. You drag the 16-pixel block and drop it between the text layers. You drag the 48-pixel block and drop it above the image. The auto layout engine sees these blocks as legitimate child objects and stacks them perfectly.
But they are big, ugly gray rectangles, ruining my clean design.
This is where the magic happens. You select all of your spacer blocks and you turn their opacity down to 0%.
They vanish visually, but structurally, the auto layout engine still calculates their physical mass. They hold the layout open. You get the absolute aesthetic control of custom, irregular spacing, while retaining 100% of the automated reflowing power of auto layout. If you delete a paragraph, the invisible blocks just slide up dynamically.
It is a phenomenal technique, but it raises a critical technical distinction regarding how Figma handles visibility within the Flexbox flow. Let us say you have a small warning badge, a red circle with an exclamation point sitting inside an auto layout card. You want to create a variation of this card where the warning badge is not active. In the Layers panel, next to the warning badge layer, there is a small icon shaped like an eye. If you click that eye icon to hide the badge, what physically happens to the layout?
This is where auto layout feels alive. If you click the eye icon, the badge doesn't just turn invisible. The auto layout engine actually ejects it from the mathematical flow entirely. The object completely vanishes from the layout calculation. The surrounding elements immediately detect the sudden vacuum of space and aggressively snap together, absorbing the empty gap. It is perfect for creating dynamic components that collapse cleanly when certain elements aren't needed.
Exactly. The layout recalculates as if the object no longer exists. But what if you were using our 0% opacity spacer hack? You want the gap to remain empty, but you want to hide the object that was creating the gap.
If you click the eye icon on a spacer block, the block is ejected from the flow, the layout snaps shut, and you lose your carefully crafted 48-pixel gap. To maintain the structural gap while making the object invisible, you must use the opacity slider and bring it down to 0%.
The object becomes visually transparent, but it violently holds its physical ground in the layout engine. Understanding the profound architectural difference between a hidden layer, which collapses the layout, and a zero opacity layer, which holds the structure open, is a hallmark of a truly mature Figma designer. It is the difference between a brittle file and a bulletproof component.
Okay, we have zoomed so incredibly far in. We started with microscopic atoms, we organized them, we bound them inside rigid frames, we set up mathematically perfect constraints and grids, and we automated their behavior entirely with the Flexbox logic of auto layout. We have built robust, unbreakable, responsive components. But here's the reality of our jobs. An app is not one button. A design system file might contain 500 individual components spread across 80 different screens, documenting 3 different user flows. As your files grow to this massive scale, how do you manage the macro level? How do you organize a project so an entire team of designers and developers can actually navigate it without losing their minds?
That is the ultimate crucible of a design system. You can engineer mathematically flawless, unbreakable components, but if a junior designer cannot find the primary button when they need it, or a developer cannot locate the final approved screen amidst a sea of rough drafts, your immaculate system is fundamentally useless. This brings us to Section 6. The macro ecosystem: pages, thumbnails, and links.
Let's start with pages. In Figma, a file is not restricted to a single, endless canvas. You can create multiple distinct pages within a single file environment, accessible via a sidebar menu. The source material provides some genuinely fascinating case studies on how top-tier tech companies utilize pages. I expected there to be one universal right way to organize a file, but it turns out it is highly cultural.
It is entirely dependent on the specific workflows, friction points, and culture of the team. Let's examine how Dropbox structures their massive design system files.
This one surprised me. Figma has a built-in feature called the Assets panel. It is essentially a search engine on the left side of the screen, where you can type button, and it shows you all the buttons in your system so you can drag them out. You would assume a giant tech company like Dropbox would rely exclusively on this semantic search, but they don't. Instead, they use pages to create what they call sticker sheets. They dedicate one massive page entirely to typography styles, a separate page entirely to buttons, another page just for OS-specific icons.
They manually construct visual galleries. And the reasoning behind this is rooted in deep internal user research. Dropbox actually studied how their own designers interacted with the software. They discovered that a massive segment of their team actively hated digging through the semantic assets panel. They experienced friction trying to guess what a component was named. Was it button primary large or primary large button?
So semantic search was slowing them down.
Yes. Creative professionals are, by nature, highly visual creatures. They vastly prefer to navigate to a massive sticker sheet page, visually scan the canvas, instantly recognize the exact shape and color of the button they needed, and physically copy and paste it into their own working file. Dropbox recognized this behavioral psychology and optimized their entire page structure to serve as highly scannable visual menus, drastically reducing friction for their team.
That is such a pragmatic approach. Serve the actual behavior of the user, even if the user is your coworker. Now, Spotify takes a completely different approach because they are solving a different problem, managing active product work across dozens of designers.
Spotify tackles the classic, terrifying problem of version control. Where is the final design? If you have 10 designers working on 10 different files exploring a new playlist feature, chaos ensues when engineering is ready to build. Spotify enforces a strict architectural rule. They utilize a single, centralized source of truth spec file per product area.
One massive file to rule them all.
Yes. And inside that centralized spec file, they use pages to represent individual shipped features. As a designer explores wild, unapproved ideas, they are encouraged to be messy in their own personal files. But once an executive decision is made and a design is locked, the designer must migrate that final approved layout into the centralized spec file onto the correct feature page to permanently document the decision for the developers. The pages act as an official ledger of shipped work.
And then there is the chronological approach, utilized by Brian Levin and Marshall Bach. the host of the Design Details podcast. Brian uses a brand new, separate Figma file for every single version release of an app. So there's a file for version 2.4, a file for version 2.5, and inside that specific file, the pages represent the exact features being tackled in that specific development sprint.
It creates an immaculate historical archive. If 2 years later, a developer asks, why did we change the login flow? You can open the specific version 2.4 file and see the exact context and pages from that moment in time.
But Marshall Bach has my absolute favorite tactical trick for managing pages. The text list of pages can get overwhelming to read, so he uses hard, visual dividing lines, just typing a string of dashes as a page name to create sections. And more importantly, he uses emojis in the page titles to communicate the status of the work instantly. A rocket ship emoji next to a page name definitively means this work is final, approved, and ready to be shipped. A magnifying glass emoji means this is just an exploration sandbox, do not write code based on this.
Emojis are incredibly dense metadata. They communicate complex operational status at a glance, breaking through scanning fatigue and instantly answering the developer's most pressing question. Am I allowed to build this yet?
But even if your internal pages are perfectly organized with rocket ships and neat dividing lines, there is still one massive macro-level problem: the Figma file browser itself. When you boot up the application, you are greeted by a dashboard grid of all your recent files. By default, Figma just takes whatever random artboards are sitting on the first page of your file and shrinks them down into a tiny, blurry, unreadable thumbnail image. If you have 20 projects going, your dashboard looks like a chaotic collage. It is impossible to tell what file is what.
It is a massive pain point that introduces immediate friction before you even begin working. But there is a built-in solution that an alarming number of professional teams severely underutilize: custom file thumbnails. You do not have to accept the blurry collage, you can actually design the cover of your book.
The source material provides the exact technical specifications for this. Inside your file, typically on a dedicated cover page, you create a frame with the exact dimensions of 1920 pixels wide by 960 pixels tall. Now, because Figma's file browser resizes fluidly depending on whether the user is on a laptop or a huge monitor, the extreme outer edges of that frame might get cropped off. But the center 1600 pixels is the uncroppable safe zone. It will always be perfectly visible.
You design a clear, bold, highly legible cover within that safe zone. Once designed, you right-click the frame and select the option Set as Thumbnail. Instantly, that design overrides the blurry, auto-generated image in the file browser. Your dashboard transforms from a messy collage into a beautifully organized, highly legible library.
And the book strongly advises not just making these pretty, but standardizing them. You should create strict team templates for these thumbnails.
Function over aesthetics.
Absolutely. The thumbnail shouldn't just have a cool gradient. It should feature a massive, bold typography title for the project that can be read from across the room. It should have a highly visible status pill-like, a bright green box that clearly says "in development," or a stark gray box that says "archived." It should include the JIRA ticket number or the sprint iteration. If your entire design organization uses the exact same layout for their thumbnails, nobody will ever accidentally open, edit, or pull code from the wrong file ever again.
It brings absolute instant clarity to the project level. And the final piece of this macro ecosystem, the connective tissue that binds all of these files, pages, and components together into a usable web, is the link system.
We are so conditioned to think of hyperlinks as a web browser feature, something you use to jump from Wikipedia page to Wikipedia page. But Figma allows you to embed that exact linking behavior directly into your canvas using the keyboard shortcut Command K. You can highlight a piece of text, say a note to a developer that says, "See API requirements here," hit Command K, and paste a link to an external Google Doc or JIRA ticket.
But the true power is internal routing. You can link to other elements within the Figma ecosystem. You can right-click any frame on any canvas, select Copy Link, and paste that link onto a text layer or a button located on a completely different page, or even inside a completely different file.
You can effectively turn a static Figma file into a fully navigable wiki. Imagine creating a table of contents page for your developer. Instead of them having to hunt through the layers panel, they just look at a list. They click a text link that says "Forgot password flow," and Figma instantly teleports their camera view directly to the exact frame buried deep on page 4 where that flow is mapped out.
It completely revolutionizes the handoff process. You are no longer handing an engineer a messy blueprint and asking them to find the bathroom. You are giving them a guided tour where every door opens exactly where it needs to.
Okay, we have covered an immense, almost overwhelming amount of ground today. We started at the atomic level, staring at a messy canvas. We learned how to mathematically align the chaos using distributed spacing and the intelligent grid deduction of the tidy-up tool. We felt the relief of sliding elements around flawlessly using the pink rings of smart selection.
We tackled the great philosophical divide between legacy groups and modern frames, establishing definitively that frames are the adaptive, property-holding, clipping Tupperware containers of modern UI design. We learned to navigate them quickly using Deep Select and how to avoid the auto-nesting trap using the spacebar.
We pinned our designs down with constraints, preventing distortion when screens stretch. We explore the rich history of layout grids, bringing mid-century Swiss graphic design and Ethan Marcotte's fluid web principles into Figma to create mathematically flawless 8-point systems.
We revealed the undocumented magical synergy of combining stretchy layout grids with constraints to maintain perfect, unbreakable gutters. We ensured our designs survived the transition to code by using the Redlines plugin to hardcode dimensions and establish a pixel-perfect handshake with our developers.
Then we brought in the heavy machinery. We surrendered manual control to the Flexbox paradigm of auto layout, allowing our designs to dynamically adapt to their content using direction, resizing, padding, and spacing. We unpacked the deep psychology behind the reverse layer order controversy, learned how to use text blocks as dynamic engines, and mastered the brilliant 0% opacity spacer hack to defeat uniform gaps.
And finally, we zoomed out to the macro level to manage the ecosystem. We organized our files using pages, analyzing the visual psychology of Dropbox and the strict version control of Spotify. We designed custom 1920 by 960 thumbnails to tame the file browser and utilized links to weave our canvases into navigable wikis.
It is the ultimate foundation for anyone building a career in this space. Once again, all of this incredible, deeply technical knowledge serves as an expansion of the Creating Layout chapter from the definitive resource, Designing in Figma, a masterclass in modern interface design. I cannot recommend picking it up highly enough. And please hit that follow button. Follow the show for more technical design breakdowns and career-building content. We love unpacking these massive systems so you can build better products.
Before we sign off today, I want to leave you with a final overarching concept to mull over. In this industry, we spend virtually all of our time obsessing over the user experience of the final product we are building. The app on the phone, the website in the browser. We care deeply about reducing friction for our end users. But I want you to look back at every single technique we discussed today. Using auto layout so a button doesn't break when a copywriter types a longer word. Using custom 0% opacity spacing hacks to keep layouts mathematically sound but visually readable. Using emoji-coded pages to signal project status instantly. Designing custom thumbnails so a specific file can be found in a fraction of a second.
It is all just usability.
Exactly. Have you ever considered that the way you architect and organize your Figma file is actually your very first true user experience design project? Long before your app hits the App Store, your Figma file itself is a product. And the users of that product are your fellow designers, your product managers, and your developers. If you build a chaotic, brittle house of cards, you are actively providing a terrible user experience to your own team.
Wow, that brings us right back to the original thought. We do not want to just nail drywall to a tree and hope it holds. We want to build a house with a solid logical foundation where the structure is unbreakable, the blueprints are clear, and anyone walking into it just knows that the lights are going to turn on when they flip the switch. Treat your design files like a product, designed for your team. Thanks for diving deep with us today. We will see you in the next one.